Hey folks, Professor Gray here, ready to talk to you more about one sample hypothesis testing. In previous videos, we had used the significance level and the p-value, compared them, and determined whether or not to reject or fail to reject the null hypothesis based upon that comparison. In this video, I'm going to try another approach. An alternative way of conducting a hypothesis test is to compare the test statistic versus the critical value or values. The critical value or values are the z-scores or t-scores that separate the area in the tail or tails from the rest of the distribution that's being used. If we're conducting a one-tailed hypothesis test, we'll have one critical value. If we're conducting a two-tailed hypothesis test, we'll have two. In this particular example, we have two tails, so we'll have two critical values to compare our test statistics to. So let's do that for their running example. We'll find any critical values and the test statistic. In this particular hypothesis test, we're using a normal distribution. An alpha was 0.05. So there will be half of alpha in each tail because this is a two-tailed hypothesis test. Now if I were only using one tail, then I would have all of alpha in that one tail. But because this is a two-tailed test, the tails will share the significance level. Now I'll find the critical values that coincide with these areas in each tail. Then I'll compare my test statistic to the critical values, and I'll see if the test statistic falls in the tails or in the rest of the distribution. If it falls in one of the tails, then I'll reject the null hypothesis. Otherwise, I fail to reject it. So the remaining area in this distribution would be 95% or 0.95. To find the critical values that coincide with that, I'll start with the one on the left. If I go to my calculator, go to second vars and inverse norm, put in my area to the left on the left tail, 0 and 1 since this is a standard normal distribution. Then I get my left critical value. It's about negative 1.96. For the critical value on the right-hand side, I'll need the total area to the left of that z-score. That would be 0.95 plus 0.025. So I would be doing inverse norm for 0.975. That's the total area to the left. 0 and 1 for the mean standard deviation respectively. And I get the positive version of 1.96. I'll compare the z-score I got from my sample data to these critical values and see if I fall within a tail or not. To find the critical value, I could use one of the formulas from the previous slides, or I can use the calculator. If I use stat, test, and 1-prop z-test, and conduct my hypothesis test just as I did when I was comparing p-values to alpha, then on the output screen, third line down, I'm given the z-score. This is the test statistic. So for this problem in this sample, my test statistic is going to be about negative 4.1. Should be somewhere in this left tail. If my test statistic, the z-score, falls within one of the tails, then I reject the null hypothesis. And in number 8, that's exactly what I'll do. Now notice, when I compared the test statistic to the critical values, I still came up with the same answer as when I compared the p-value to alpha. This is just an alternative way to arrive at the same conclusion. Either way, we rejected the null hypothesis. And when that happens, the sample data is often called statistically significant. Statistically significant means that it's just too unlikely or too rare for this result to have actually happened by chance. If we fail to reject the null hypothesis, then the sample data is not statistically significant. Now, our results may be significant in some other way, but not statistically so. They're not rare enough for us to use the rare event rule. Well, if we were to reject the null when it was actually true, then that's called a type 1 error. If we fail to reject the null when it is actually false, that's called a type 2 error. For example, if we rejected the null and 2 years later another study revealed we were wrong, that would be a type 1 error. Now, if we failed to reject the null and then 2 years later another study revealed that we were wrong about that, that's a type 2 error. Alpha, the significance level, and the area in the tail or tails of the distribution, is also the probability of rejecting the null hypothesis when it was actually true, or a type 1 error.